Avi Wigderson, and he received Nimalina Prize in 1994 for profound contributions to diverse areas of mathematical foundations of computer science, including complexity theory, zero-knowledge proofs, and the study of computational power of randomness. And in 2021, he co-shared Abel Prize with Laszlo Lovich for their foundational contributions to theoretical computer science and discrete mathematics, and their leading role in shaping them into central fields of modern mathematics. Avi, please.
Oh, the lights are really bright here. Okay, hi everybody. I hope everybody can hear me well. I want to tell you about this title, Imitation Games. Basically, it's a framework, a paradigm suggested by Turing, and with some hindsight, turns out to have cropped up in various fundamental areas within theoretical computer science, which is my field. So let me start. The plan is simple. I'll tell you about Turing's original imitation game. Some of you have seen it in the movies, how to test intelligence. And once we have this framework, I'll go into the more modern imitation games that really are crucial for central definitions of notions in cryptography, in randomness, in discrete mathematics, and in the study of privacy. There are many more. I'll just do these four. They are big areas, and I will just, of course, devote only a few minutes to each, but hopefully showing you how this paradigm affects this. And part of it will be about how important definitions are in science, in mathematics, even before you do more. Then we conclude. So that's a plan. So I'm going to talk about Turing's work. Let me just say a few words about this great man. As you see, he had a short life with a tragic end, and during it he managed to do amazing things. He's in one paper as a graduate student, he at the same time started both the computer revolution and the scientific field of computer science that we are all experiencing the amazing growth and importance of. During World War, he, of course, was in the team cracking the Enigma machine. Few know that he wrote extremely foundational papers in biological modeling. He was interested in everything. And what I refer to now is his work on artificial intelligence. So in 1950, he wrote this paper, Computing Machinery and Intelligence. And well, I would recommend anybody to read any paper of Turing. He writes with such clarity that it's irresistible. And in this paper, he basically says the following thing. I want to study the question, can machines think? Of course, today is very popular. At the time, it was not so many. There were not machines much to speak of that you could imagine this for. And he says, well, I could start by, the philosophical, ontological approach of just defining these words. What is a machine? What is to think? And then we'll get into lots of argument. Instead, I'm proposing, let's just test if a machine can think. Okay, that's the operational or behavioral definition. And the general point is that, objective definitions of things complicated like intelligence or cognition and so on, maybe, may not be testable, may not be falsifiable, may not have a universal meaning for anybody. And subjective behavioral definitions sometimes can be made very precise, testable, operational, useful, and we'll see in the examples I'll give later, revolutionary. So I want to start from his imitation game, which is this how to test intelligence, and then we'll move to the more formal ones. So what was the idea? You want to test whether some entity, maybe a robot, a software package, is intelligent. Intelligence can stand for, can converse with humans or any property like that. And the test is you set up two possible worlds. There is some referee, some human referee in this case, that is interacting with one of these entities, and it doesn't know whether it's the human or the robot, ask questions or whatever through some medium, converse with that entity, and at the end decide something. You know, I believe that's a human, or I believe that's a robot. Some binary decision. And of course, if, you know, in both cases, these two worlds, the behavior of the referee is the same, then we may say that, oh, that's an intelligent robot. Of course, and if, you know, there are different answers, then we say maybe, we identified, distinguish the human from the robot. But this is too simplistic yet because, of course, every referee may interact many times with the robot, and the decision may be just some confidence level or statistics. So they may say, oh, in this case, I am sure with 92% it's human. Or, and still we would like this. If these answers are very close, then these two worlds are indistinguishable. The robot, you know, succeeds at fooling the referee. Or if they are very wide apart, then you know, you caught them. So what we really want to say, and of course there could be different referees who may have different confidence levels, but if they always come up close in both worlds, then we want to say the two are indistinguishable. And so we would define, in this case, the robot is intelligent or the robot can converse, you know, if for every test, for every human referee that is quizzing them, the answers are very close to each other, these percentages, these numbers between 0 and 1. This is a template. This is a template we'll see again and again in different fields. But that's the idea of the imitation game. You just want to test whether two things are equivalent according to some family of tests. And how close these are, there are of course lots of parameters I will not get into, but you want to say they're either very close or far apart. This, you know, mountains of words and papers were following Turing's paper, and I'm not going to talk about them. Some of them talk about whether, you know, it's a good test, not so good test, how to revise it. There are lots of implementations, there are Turing test competitions, and so on. And I also am not going to look at extensions of this intelligence test to other, you know, qualities that you want to compare machines and humans, like whether they can have emotions, whether they are conscious, or whether they can be creative. You know, there'll be plenty of ML and AI discussions later in the, you know, this afternoon and later. I'm not going to talk about this. What I want to talk about is precise or formal imitation games and how they influence areas within the theory of computation and discrete mathematics. The paradigm is like we saw before. Two things, whatever they are the same if they cannot be told apart by, you know, tests that are reasonable for the task. And reasonable depends on whatever, the application, the theory you are trying to build, and so on. You'll see very different ones. And one point I want to stress is having the right definition of some central notion is primary. If you get this to work, if you do it, then, you know, theorems, proofs, constructions, theories usually follow. You just have to get the definition correctly. And we'll see in this talk, I'll just talk about definitions that have the structure of an imitation game. And then we'll see how they enable this progress in math and, in fact, science and technology and policy as well. Okay. The first area I want to discuss is cryptography. Again, each very briefly. Cryptography existed for millennia and mainly focused on encryption, hiding secrets. Say you are in a situation like a battle, and maybe you're a general, you want to, you know, give an order either to attack or retreat. You want your troops to understand it, but you want the enemy not to understand it, and so you encrypt it, you hide it using some encryption function. And you know, there are many that exist. You know, the Caesar cipher from 2,000 years ago is just a simple letter substitution. That's actually the one I used in encrypting this. Much more complicated one that I mentioned, the Enigma machine, where it's also letter substitution, but it's time-dependent, message-dependent, key-dependent, and yeah, anyway, more complicated. There are many encryption functions. And the basic question of cryptography with respect to encryption is it secure? Does it do what it should? And a more basic question is, what do we mean by a secure encryption function? How can we define it? And it took 2,000 years. It took till 1981, till two, again, graduate students, Goldwasser and Micali, proposed the following. And you'll recognize this two-world situation. We want to know whether we cannot distinguish the encryptions of two messages. So let's take any two messages, and we are testing the encryption function here. What do we want? What's the best we can want? We want that nobody looking at them can tell them apart. That's the highest you can do. Say any algorithm, any efficient algorithm looking at these two encryptions and produces a guess whether it's a zero, it's the first or the second, gets the two numbers very close, cannot really tell them apart in this sense. So we say that this encryption function is secure if for every two messages and every efficient algorithm, this test that is trying to distinguish them, these two numbers produced will be very close. Okay, so that's very natural, but in fact it's very strong. I mean, it's sort of shooting for the moon. It's the best you can hope for. You don't want anybody to even distinguish the two slightly, and any two, like maybe an encryption of 0 and 1. This is a fundamental definition, change the face of cryptography. First of all, it's a formal definition of what a secret means. And it actually, you can see from the definition that no deterministic encryption will pass this test, because you will try just the two possibilities. Encryption must be probabilistic. This follows from this definition. And the second part of any your good definition is they show that it's possible to achieve, despite the fact that it's so strong, it's possible to achieve, and it relies on a simple mathematical hard assumption. For example, the assumption that factoring integers is difficult. And this is, of course, what you use every day when you shop online. So this definition has a template of an imitation game. And once this existed, the theory of cryptography took off, and people tried to build, find protocols, not just for encryption, but for many, many other tasks. Online shopping, contract signing, secret exchange, zero-knowledge proofs, online elections, blockchains, lots of many things are not listed there. You want to do all of them without any physical implement on the internet. And the question for each of them is you design a protocol, the analog of what we had encryption. You design a protocol for the parties interacting, and you want it to be secure. And again, the question is, what do you mean by secure? And again, in each of them, if you look at the definition, you will find that it's set up, again, with hindsight. I don't think it's written explicitly in any of these papers. But in hindsight, it's set up as an imitation game where you compare what happens during the actual execution of your protocol to what would happen in some ideal situation. Maybe you have trusted parties and anything you want to assume about the ideal case in which you know that nothing leaks, it's secure, and so on. You want to say the ideal case and what happens in the actual protocol are indistinguishable to any algorithm. And this is what is done in all of them. I'm not going to elaborate, and that's, of course, it's a major field with major impact on our lives. I want to switch to, I'll delay questions to the end, if it's okay. So I want to talk about randomness, and in particular, the fact that having randomness is great. So, nature seems to supply us with perfect randomness, like, arbitrary sequences of unbiased independent coin tosses. And if we have it, then we have lots of things. There are many applications of this, sampling, scientific experiments, probabilistic algorithms, crypto, game theory, gambling, many others. I want to focus on probabilistic algorithms here. And the main thing that we observed the last 40 years is that having randomness for algorithms for computation is extremely powerful. I mean, we seem to be able to solve lots of problems with probabilistic algorithms that we cannot solve deterministically without probabilistic algorithms. And of course, that's great, and we use them all the time, but there's a fundamental question there. Do we really need them, or can we do without them? This is particularly important because it's not clear where do we get these perfect random numbers, right? There are many sources, but are they what we think they are? Are they how we analyze the algorithms with? So I want to suggest three possible worlds and compare their power with respect to probabilistic algorithms. One is the one we started with, in which perfect randomness exists and is accessible to us, and we can do these things. Another one, which is maybe more realistic, is that the world is full of unpredictable phenomena, maybe the weather, maybe stock market fluctuations, sunspots, quantum phenomena, I don't know, which produce, if you sample them, they produce some sequence that is probably unpredictable, like we don't know what the stock value of Microsoft will be tomorrow, or what the weather will be tomorrow, but maybe there are correlations to what it is today. So it's a sequence of biased and dependent bits. It's not perfect randomness. What can be done with this? Can we run probabilistic algorithms with this? It's just distributions with some entropy in them. And the last world is, what do we do if there is no randomness at all? Maybe the world is deterministic. Are the probabilistic algorithms any good? Can we do anything? So, yeah, we saw that. And let me tell you how we answer the other two questions with actually pretty surprising answers. What we need to understand is, what kind of quality, when is the distribution useful as if it was the uniform distribution, the perfect randomness. So we want to define the quality of an arbitrary distribution as being pseudo-random, random enough. And that came again in seminal papers in the 80s, Blum and Micali and Yao, which define it using an imitation game. I'm sure by now you could all do the definitions yourselves. When is a distribution as good as perfect? Well, if it fools every possible algorithm. If you feed it to any algorithm and it's supposed to guess whether it's one or the other, or it just has a binary output with some probability, we call it pseudo-random if, regardless of which algorithm you try to distinguish them from, they give the same, roughly the same output. So then, then it's as good as random, right? Pseudo-random is as good as random. This theory, again, is extremely powerful, extremely broad. Having a formal definition allows for composition, amplification, and leads to this hardness versus randomness paradigm that I'll tell you in a second about. And of course, has many, many practical applications. But let me answer the questions about these three possible worlds. So, weak random sources with some entropy, I'm not going to define exactly how, can they be used in probabilistic algorithms? It turns out the answer is yes. It's highly non-trivial. You cannot just feed this distribution there. There are clever ways of purifying or amplifying the entropy in any such distribution. This is called extractor theory, randomness extraction. And the upshot is that you can run any probabilistic algorithm using these sophisticated tools with very weak random sources. So we don't need perfect randomness. Now, what do you do if you have no randomness? The world is deterministic. What do you do with probabilistic algorithm? What do you feed it? Well, here, it turns out you can still do something, but you need an assumption. The assumption is something we all believe, that P is different than NP, or that some hard functions exist. Why do you all believe it? Again, because of crypto, right? You all believe that factoring is hard, or something protects your online shopping. So assuming that some problem is hard is an even weaker thing. And it turns out that under this assumption, some hardness assumption, you get again that you don't need randomness in probabilistic algorithms. You can trade off hardness and randomness. One way to phrase it more precisely is that every probabilistic algorithm that's efficient in existence can be replaced by a deterministic one of roughly the same complexity. Okay, so again, randomness is much weaker for algorithms than we would have thought, given all the examples that we can solve fast probabilistically and cannot deterministically. Okay, that was my second one. I realize it's lots of context switching and it's fast, but that's the time allotted. These are, by the way, major theories, and besides these consequences, there are many unexpected benefits to them that I will not talk about. And I want to switch to still talk about pseudo-randomness, but not from a computational point of view, but from a structural point of view, which affects discrete mathematics and number theory, and you'll see even more. And the context, there are several, and the context I want to focus in is things of the type of Ramsey's theorem, which, sort of philosophically or at high level says that there is no chaos in the world. Every system, every large structure, no matter how complex, has some substructure which is extremely nice, much nicer than you would expect, maybe. And particular example is this one. So I want to define periodic sequences. You probably all know what it is. So I listed here all the integers. Well, not all the integers. It goes on to infinity. A periodic sequence is just a regular sequence, an arithmetic progression. So I have 7, 11, 15, 19, and so on the top, and then with gaps of 7 in the bottom. These are regular patterns, periodic sequences, and of course the integers have them plenty because the integers themselves are periodic. But suppose we take a subset of the integers, some large subset of the integers. Do we expect that it will have a periodic sequence, subsequence? It's not clear. Suddenly these two examples, they are not there, but if this is long enough, dense enough, maybe it does. So that's the question, which subsets of the integers have long periodic subsequences in them? That's a question, and this was answered amazingly in the positive by Andrew Semeredy in 1975. Every dense subset, no matter how adversarially constructed it is, has an arbitrarily long arithmetic progression. So if you pick any way you want, every thousandth integer, right, about, any way you want, and it will contain a periodic sequence of length, any length you want, 100, 1,000,000, trillion, there it will be there. It's an amazing result, and I want to say something about the way it is proved and the definition that's key to that proof. You may, be interested even in sparser sequences, that dense sequences, like a constant fraction of the integers. This subset you recognize is the primes, and you can ask whether, this subset contain arbitrary, long arithmetic progressions, which sort of seem to conflict with the idea of primes. But the famous Green-Tau theorem, building up on Semeredy, shows that also there you have long arithmetic progressions. So what goes on in these theorems? The starting point is that if you have a random subset, if you pick every 1/100th of the, every integer is picked with probability 1%. It's random, independently. This will have long arithmetic progressions with high probability, and that's really easy to see. So random subsets do, but we want to say all dense subsets do. That's Semiradis theorem. So we want to understand which subsets look random. And Semiradis theorem really proves that every dense subset, if you take any constant fraction of the integers, it looks random in a particular way that suits this theorem. And to prove this result, he switches magically to not talk about subsets of integers, but about graphs. He says that also every dense network, every network with many edges, looks random. So I want to explain what does it mean, this look. Okay, and then, he proves this theorem by, and with another magic trick. But I want to focus on what does it mean to look like it's random, for a structure to look like it's random. So we have to understand what a network is, what clusters are, and what bonds are. A network, you know what it is. It's just a, it can be a network of rows or internet or Facebook, network of friends. It's just nodes with pairs connecting them. Some pairs exist, some don't. What is a cluster? A cluster is just a subset of the nodes. Okay, that's one cluster. And bonds are between pairs of clusters. So you take any two clusters, any two subsets, and the bond is simply the fraction of edges between these two subsets. Okay? This number between 0 and 1 is a fraction of connections between these nodes in the first, nodes in the second. Okay, that's the bond of a pair of clusters. Now, I want to define when are two networks bond similar. Okay? Again, an imitation game. You have two arbitrary networks and you have 1 million nodes or 1 billion nodes. Same number of nodes in both of them. We want to say they are bond similar. Again, we have a sequence of tests. The tests are just the bonds. We take any two clusters, the same two clusters in both, and we look at the bond. We look at how, what's the fraction of connections between them. And if for every pair of bonds, if for every pair of clusters, the numbers are essentially the same, then we call them bond similar, this pair of networks. Okay? So it's an imitation game definition. The set of tests is pairs of clusters and their bonds. And then comes with this definition, and Semiradis proves his famous regularity lemma. So I want to explain the regularity lemma, saying basically that every network looks random. So I want to explain in what sense using this definition. So every network is bond similar to a random network. So what does it mean and how is it done? The way it's proved is that, I want to explain what is this random network. The core is that every network possesses a tiny description of it that can fit a random model. Every network has a tiny model. And it comes from the fact that magically, it's sort of very counterintuitive. If you know the bond between very few clusters, you know all the bond values for all clusters, all pairs of clusters. So basically, there's always, what it proves is that always a partition to a few subsets of your graph, of your network. And if you just know the fraction of connections between these pairs, like I have red, green, and blue, and you know this fraction, then you know the bonds for all the other structures. It's sort of amazing. And then you can construct a random network from this tiny model in the obvious way. You take red, green, and blue and connect within the red according to their fractions, 0.8, within the red and blue, 0.1, so on. And you get a random network, and it turns out what it proves is that these two are bond similar. So every network has a random model, and for random structures, you can prove what you prove easily. I want to say that this idea took off big time, and we talked about dense graphs, dense sequences, but in fact, any set of objects you can, and any set of tests, almost, you can run this idea for. This leads to what's called the structure versus randomness dichotomy. That is a very powerful tool, both in mathematics and computer science, and is now used to give proofs to many theorems in lots of different areas in this field. Okay, so now the last topic. I want to talk about privacy, and we'll see again a demonstration of this powerful paradigm of Turing. Privacy, there is always a trade-off with utility. If you don't care to use your data, then you can hide it and never show it to anybody. So data, I want to think of a database, many individual records. It can be census, data, medical data, whatever. Once you have data analysts that want to analyze the data and get some valuable conclusions from it. And the utility of this activity is, of course, obvious because maybe you learn about social things, welfare gaps, urban planning for these individuals, or maybe if it's medical, you get information about drugs and good treatments. I mean, it's very valuable to analyze data. On the other hand, we want privacy. If you are an individual, let's say Jane Doe here is one of the records, she may ask herself, should I participate in this study, or should I tell the truth when they ask me questions, and so on. So this is a trade-off you have to make. And of course, this is an old problem, was studied for 50 years at least since big databases exist. And many ideas came up to restrict the type of queries, maybe to statistical ones, to filter answers by noise, and so on. And it was never really formalized, I would say, well, certainly not in the way I'm going to describe, so you just want to answer not the values in the database, but some noisy version of that. How do you formalize this? And you formalize it again in this seminal paper from about 5-6 years ago with an imitation game. This is called differential privacy. What you want to study is pairs of databases that differ only in one entry, let's say the entry of Jane Doe. Okay, these are called adjacent databases. And what do you want? Again, like always, you want them to be indistinguishable to whether Jane Doe was in the database or not by any query that's allowed in your system. And if for any query the answer is roughly the same, then Jane Doe should be happy, right? So it guarantees individual privacy. So that's at least the definition. Filter and noisy version of data provided to queries is differentially private if for any two adjacent databases, so when you remove or add only one person, and every legal query, what the output is the same in both worlds. And moreover, they develop, filters which satisfy this definition. And this, so it leads to a lot of theory that's really interesting and powerful, but moreover, it was really adopted. I mean, adopted big time shortly after it came out, both by big companies like Google, Facebook, Amazon, who have, of course, enormous amounts of data and are releasing parts of it to data analysts. It was also adopted by the US government, and the census data from the 2020 census is released, again, according to a differentially private mechanism of the type developed here. So it practically is effective, but in my last slide, I want to show that ideas like that can sometimes, also like with cryptography and pseudo-randomness, can have an impact in areas that are, don't ask the question, in this case, of privacy. So I want to talk about adaptive data analysis and how this point of view of privacy affects basically the scientific method. So these are two papers, again, very recent. And to explain what's going on, just think about what you know is the normal process of science or of machine learning. There's a bunch of data, and there is some analyst or analysis tools, software. It can be a scientist, it can be a deep network, whatever, and it interacts with the data to understand it, right? And this interaction is adaptive, and it repeats a cycle of, forming hypotheses, tuning parameters, generating queries, getting the answers, and again doing it, and again doing it, and so on. This is how it works. So what's wrong? What's the problem? Well, the problem is you get papers that have these amazing, frightful titles like "Why Most Published Research Findings Are Wrong." So science doesn't work according to this. This is just one of many papers. It has lots of citations. That's why I picked it. But there are many articles like this. And it's very easy to understand what is wrong in this picture, in this iterative process, is that, of course, we know that data is expensive to get. So you get it, you pay for it, and then you reuse it because it's expensive. And reusing often leads to overfitting and lack of generalization of the data to what you really want to understand. You never want to understand the data you have. You want to understand the phenomena that generated the data, right? You want to generalize. The data was sampled maybe from the population or from some natural phenomena, and you really want to understand the initial issue rather than what's in the data you happen to sample. So the idea of these guys was that let's apply a differentially private mechanism to the data you have. Okay, there's no issue of privacy. There's no privacy. Let's anyway put a private mechanism there and feed the analyst only the filtered data. What they prove, it's a theoretical result, of course, it's a mathematical theorem. Using a differentially private filter, this problem goes away. There is no overfitting, statistical validity is ensured, despite the fact that data is reused. Of course, all is quantitative. You ask more questions, you get less. Anyway, so everything is quantitative. But it's sort of remarkable that in a problem possessing no issue with privacy, using a privacy mechanism, you can eliminate issues that are basically statistical. Okay, I think I've gone through all the 4 examples I wanted. Let me summarize. The main paradigm, starting with Turing, is that things are identical unless you can tell them apart. And this holds not just for my examples, but for diamonds or Picassos or news, to know whether they are fake or real. You can apply what you can apply in each case. And that's the only thing you can really know. And of course, U is a set of tests that's relevant for the issue at hand. Another thing I want to stress is that definitions of this nature, behavioral, subjective definitions, can be extremely powerful, and they can be used to study lots of other notions I didn't describe here, going back to the issues I was talking about in the beginning. And finally, what I said already twice, definitions of central notions, having the right definitions is really primary. And once you get them right, you have amazing theories and consequences, both theoretical and practical. Let me conclude with an advertisement to the book I wrote about 3 years ago. If you want to learn more about computational complexity theory and theoretical computer science, you don't have to buy it. It's free on my website. You can all, access it freely. Thank you very much. Yeah, thanks. So ask me questions. Any questions? Yeah, more light. Yeah.
Thank you for the talk. It was very interesting. I was just wondering, in all of your definitions, the subjective definitions that are sort of analogous to the imitation game, there is this idea of various quantities being approximately the same. In the different contexts, what does this mean, this approximately the same mean?
Yeah, so deciding the value of how approximate is approximate enough is very important in all of them. In cryptography and pseudo-randomness, usually you take it to be, there will be some parameters, some size n that you care about, input size or so on, and this is usually taken to be 1 over polynomial in this number. In the case of privacy, for example, it's taken to be some constant, some small constant that's appropriate, again, to the application that depends on how many queries you are going to query the database. And in the case of the structure versus randomness, like the Semeredy theorem, it's tuned to the problem. It's very tuned to the way you are searching for, 4-term arithmetic progressions in some subset of size, I don't know, 1,000th of the integers, then you have to pick it right. This is a very important thing that you have to, it's attuned to the application. There is one here.
Okay, may I speak or?
Yeah.
Microphone here. Avi?
So, yeah. Oh, sorry. Yeah.
So you stress the importance of giving definition, but actually there is a process, a moment in the process which is very important, which is to identify that some notion may be relevant, and which I think is very often hidden, because quite often it takes sometimes even centuries to identify that something is relevant, and then, of course, giving a good definition is very important. But earlier in the process, I think there is also this issue.
Yeah, I completely agree. I mean, it's just that in some cases, these notions are burning for having a definition, like privacy. It's not saying that this particular definition is the only one or the right one, but what is a secret, how to hide secrets from others. These things existed for millennia, and people know it's an issue to get them right. And then you need to get them right. So, but I agree, sometimes, and mathematics is full of examples like that, where we don't even know what we need to define. But once you know what you need to define, you also need to get the right definition. Thanks. Yeah, I mean, maybe you choose them. It's a better than yeah. Why don't you choose who is, I don't know, who will speak next?
Hey.
Yeah.
Hi. Thank you for the lecture. And my name is Jim Abdulgani. I am Nigerian. I am a master student at School of Collective Intelligence in Morocco. My question to you is, you make mention of something about my Turing machine and Enigma machine. Last month, I was in Tunisia for AI hackathon organized by Instant Deep Company, and a problem was given to us to solve on Enigma machine, and a lot of data set was supplied to my team to detect fraud. But my question now, we built the model, but we didn't win the competition. But is there any relationship between Turing machine and Enigma machine? Please, can you share more light on that?
Yes. So the Enigma machine is just a particular piece of, software or hardware. It's an algorithm. It's a particular algorithm to encrypt messages. It's not perfect, as we know. Turing machine is a machine that's capable of running all algorithms. It's a general model of computation. So it's just, they live in two different levels. The fact that, they both are called machines is, is a chance. Yeah, it's, deciphering the Enigma machine is not an easy task even after the fact that we know that it was broken. So I'm sure that, this competition was interesting anyway. Turing and his team worked hard.
Yeah, my second question is on Enigma machine. Is it a good idea to using machine learning model to solve problems that are related to Enigma machine, like in encryption of data? Is it really good? Because this is one of the problems we face in the competition while trying to build a model to, we want to build a model that will supersede the Enigma machine in terms of encryption.
Yeah, so I think, it seems like running machine learning on almost anything is always a good idea because it seems to work in lots of problems. I don't know whether this is something that will break, current cryptographic systems as opposed to, the Enigma machine. But yeah, it's a good idea.
Okay, thanks.
Thanks.
Thank you for the lecture. So you presented definitions like differential privacy and encryption. So I want to know, do these definitions, when applied to systems, come with quantifications of how secure the system is? And if there are quantifications, do those quantifications translate to kind of like notions of, protection duration of the system and things like that?
It's, I didn't try to, I hope you didn't understand me that this particular definition solves every problem there is. I mean, there are lots of issues with all these fields. There are big fields, and these definitions I gave you are just the first, thing out of many. Lots of issues that come up, like what you discussed, require more definitions, more refined definitions, and what I wanted to demonstrate is that many of these definitions fit the paradigm, the framework of Turing, this imitation game, and it's not obvious that they would. It's not obvious that they should, and it seems to be a common thread in many of the fields, subfields that we have, that they arise. Yeah. There should probably be several microphones so people can ask questions in parallel. Yeah.
Hi. Thank you very much for the talk. I had a question on the fact that in the examples you give for the imitation game, the domain that you perform the test on is discrete. And is there an extension of the imitation game to continuous spaces?
Yeah, so it's a great question, and I don't know. I think of the world as discrete, so I don't think we have we really have real numbers. It's a convenient metaphor to do analysis and stuff like that. But yeah, anyway, it's a good question, and I think there should be. I don't know. Offhand, I can't think of one. That's a very good question. Thanks.
Thank you.
Okay. Yeah. Yeah. I think that person has been waiting a long time.
Do you think real randomness exists? And if yes, how would you recognize it? Or are there always hidden variables?
Yeah, so beliefs are on the side, but let me say that it's often convenient for me to imagine that randomness does not exist at all, and the world is totally deterministic. It's a very convenient, I find it useful for my work. Now, the issue is serious, and there may be randomness, and people have looked into testing whether a sequence was produced at random. There are very interesting works that have to do with that actually use both quantum mechanics and the theory of randomness extraction I talked about in order to test whether things produced by quantum mechanics have randomness in them. I don't know of any test that does not require you to have some randomness already when you start. So it's a great question whether the existence of entropy in data can be tested in a purely deterministic way. Yeah, it's a great question, and it's studied and looked at, and yeah, there is no clear results to this. Yeah.
There was a question earlier whether machine learning could break cryptography. So machine learning can do magnificent things. The one area where it had been a total failure is in cryptanalysis. I'm not aware of any non-trivial example in which machine learning had managed to break any modern crypto system.
Yeah, I would even generalize it. I mean, I did say that it's always good to run machine learning on it. It's more general than this. It's not just cryptography. I think that there are many questions. I mean, cryptography rests on complexity theory, on the difficulty of some functions. There's no success that I know on sort of predicting or from examples, like when you see examples of cryptographic output, signatures of a set of messages and so on, to be able to continue them. I think that this is true for any algorithm, not just cryptographic algorithms. Lots of sophisticated algorithms, predicting them, knowing what will be the next output, things of this nature, is very hard to do, and for machine learning in particular. But yeah, I think still that everybody, including cryptanalysts like Adi, who's broke many cryptographic systems, at the end of the day, what he knows, what's in his brain, is a product of his experience, and machine learning programs can gain experience, and maybe they'll break crypto systems, and maybe they'll predict algorithms. I think the power of machine learning, of course, everybody agrees, is a great thing to explore. Yeah, but
Thank you so much for the lecture. It's quite insightful. I have a little bit of worry, and it's around differential privacy. For instance, considering the fact that it's quite applicable in many domains and even in machine learning, an area like computer vision, some areas of computer vision, precisely object detection, medical imaging, which still have relatively small amounts of data compared to areas like image recognition or face recognition. And in these areas, precisely in medical image diagnosis, I think differential privacy still comes to play, and it's quite important to protect the privacy of patients. So how do you think the relative size of data would not be a problem to differential privacy in these kinds of domain, not necessarily this domain, but similar domains with data problems? Thank you.
So, yeah, I mentioned it before to another problem. I think that these issues of particular applications and the use of them, some of these theories, whether they are relevant or irrelevant to particular applications, is something you need to work on further beyond the level at which I got to in this talk. So yeah, for your question, I don't know particularly about computer vision. No.
Thank you for your lecture. I have one question regarding the Turing machine. So recently, there has been one area, computational media and arts, where machine generates poetry, arts. But the question is always, is it creative? So can Turing machine be used to measure creativity in computational sense? So
Yeah, so it's a great question. It's one of the ones I said in the beginning I'm not going to discuss in the lecture, but since you asked, I see no particular reason that a machine cannot be as creative as human, or cannot be as conscious as human, or more, or cannot be, you know, I mean, I basically don't really distinguish myself from a machine. I feel I'm a machine, a particular machine. I like myself, so I think I'm a good machine. You know, we operate with different, maybe we're carbon-based and other machines are silicon-based, but basically we all come to life with a particular software, and then we learn, and we, later we are able to generate theorems or poetry or something like that, and I don't see any reason that other machines or other creatures in other stars, galaxies can do the same. Yeah, in principle. Yeah.
Last question.
Thank you very much for your conceptualization. It was very enlightening. And also, obviously, extremely productive. Do you have any insight about the commonalities between the concepts which can be like generalized or generalized using the idea of imitation games? Like, obviously it's about similarity, but like the point about privacy is not really similarity, but really dissimilarity. So what is it that these things have in common?
Yeah, so I mean, in this example, it's a great question, really, and I must say that I thought about, I need to give a talk last year, and it occurred to me that there are many of these definitions in these various fields in my area that fall under this common structure, but I don't know how to generalize it to say where would it be useful otherwise, or even in these examples, what exactly is common. You notice that they are actually different. Like for cryptography, we wanted two different messages to look the same. So the two sides are equal. On the other hand, in the intelligence test, maybe, or certainly in the pseudo-randomness case, there is an ideal situation, and there is something that's like a perfect, and then there is something you want to be sort of ideal. So some cases are symmetric, some are asymmetric. I don't have a theory of imitation games. Maybe there's one to be found. It's just sort of striking that so many essential definitions in so many areas somehow fit this bill. Of course, I made them fit. Maybe I pushed them into being fitted. But I find that it's striking how, visionary is this setup of the imitation game.
Thank you very much.